Good morning, all of you. In the previous class, you have learnt about the path lines and the streamlines. And remember, dj by dt is equal to j into divergent of q. This is called as Euler's formula, and you don't have proof in your syllabus. And integral over a any closed curve will be equal to 0. In the sense, for example, since C is a closed curve, if you are going to get any value, something like dx, this value will goes to 0, or dx square, this value is also equal to 0. But suppose if you have something like a d by dt of some variable into dx, remember this value will never be equal to 0. Only when you have a closed curve, closed integral with something like this is called as integral over a closed curve, and this value will always be equal to 0. And the next concept is circulation. Circulation, the meaning is circulation for any continuum is defined as it is integral of the velocity vector q taken over a closed curve C is called as circulation. Let me repeat it once again. The closed integral C taken for a velocity vector q around a closed curve is called as circulation, and it is denoted by IC or a symbol tau. Tau or IC is a representation for a circulation. So this is what the definition of a circulation is, where dx is an elemental length of a continuum. Elemental length of a continuum. Elemental length of a continuum. Now, from the Stokes theorem for vectors, you already know that as per the definition of Stokes theorem, u dot t cap dc is equal to integral over s curl u dot n cap into ds. Stokes theorem we are mainly using to convert the closed curve integral into a surface integral. So here you have a closed curve integral. Let me convert the same in terms of surface integral. So how can we write this as, just wherever the vector is there, you have to take curl of that vector, replace it with the unit normal vector n cap. So IC can be written as, q can be written as curl q. This is what the representation of a curl of a vector dot n cap into ds, where n cap is the unit normal to the surface. Now you already familiar with the vorticity vector omega. Omega is the vorticity vector. While explaining the irrotational motion, I have told you that omega is the vorticity vector given by omega is equal to curl q. Fine. Omega is equal to curl q. So I can replace, this is what the definition of a irrotational motion is. Irrotational motion. Now, so I can replace curl q with the vorticity vector omega. So I can write a definition for a circulation as vorticity vector omega dot n cap into ds, where omega is the vorticity, n cap is the unit vector normal to the surface, something like this. This will be the n cap. Now from this definition it is clear that suppose if a motion is irrotational, we know that vorticity vector will be equal to 0. Whenever the motion is irrotational, omega will be equal to 0. If that was the case, the value of IC will become 0. Why? Because when you replace omega with 0, this whole term will goes to 0. So that is how IC will be equal to 0. So we can say circulation around the closed curve is 0 only when the vorticity vector is 0. So this is what the definition of circulation is. Now the next concept is Kelvin circulation theorem. Please go through the notes while explaining. Why? Because I have not mentioned all the steps in the notes whatever given in the group. So please write down there itself if you are not understanding the steps. This theorem is asked in the year 2015, 19 and 18. So Kelvin circulation theorem. So as per this theorem states that if the acceleration is expressed as gradient of some scalar function pi, where q is the velocity. So you know rate of change of velocity will be an acceleration. Fine. So if acceleration is expressed as gradient of some scalar function, then as per Kelvin circulation theorem, the circulation remains constant. Let me repeat the statement once again. Kelvin circulation theorem states that if an acceleration is expressed as gradient of some scalar function pi, then circulation IC taken over that closed curve will remain constant. So let me prove how you are going to prove. In the statement it is mentioned that if an acceleration is expressed as gradient of some scalar function, circulation is constant. So let me take dq by dt as del pi. In the sense I am expressing an acceleration in terms of some scalar function. So as per the statement, circulation remains constant. So it is equivalent to say dic by dt will be equal to 0. Why? Because IC is constant, that is circulation is constant. In the sense, rate of change of circulation will be equal to 0. So differentiation of constant will become 0. Now from the definition of circulation, just now I have explained, it is a velocity vector q taken around a closed curve C is called as circulation. This is what the definition of circulation is. Right? Now let me differentiate this. Dic by dt will be equal to d by dt of q dx. So let me take the derivative inside. So you will get d by dt of q dx. Fine. Now you can notice that here you have two functions. So I can apply the product rule here. Let me see what happens. First function q into differentiation of second function. This is what the second function is, plus second function into differentiation of first function. Just I am applying the product rule for this one. Now you can note that q is the velocity vector here. So let me write here. So dx is the elemental arc length. Dx is an elemental arc length. So I can write d by dt of dx, d by dt of dx as q. I mean dx by dt as q. Why? Because see here, dx by dt, x is the displacement vector. So rate of change of displacement is what? Velocity. Rate of change of displacement will be a velocity vector q. So look at here. Let me write q as it is. Now you can note that dx by dt, rate of change of displacement with time will be q. So this d let me write as it is, differentiation of q. Got it? Let me repeat this step once again. So dx by dt is the velocity vector q. So let me replace dx by dt as q. I will retain derivative as d as it is, plus let me write this as it is, dq by dt. Fine. Now you can note that this term can be written as half into derivative of q square. Why? Because if you differentiate this, see, half into differentiation of q square is 2q dq, right? Half into differentiation of q square is 2q into dq. 2 get cancelled, you will get q dq. So this is what you have here. So I can write this term as half into differentiation of q square plus dq by dt into dx. Got it? This term here, this term here. Now I have told you that half is a constant, so I can, let me write one more step. Half outside I will write c differentiation of q square. Integral, I am going to split the integral as per the property of integration. So integral split ಮಾಡಿ. Now you know that the integral over a closed curve is 0. Just now I have told you. So this term goes to 0. So what you left with is dq by dt into dx. So in the LHS what you have? dic by dt. So dic by dt we can write dq by dt into dx. Now what I have assumed from the equation 1, velocity can be written as gradient of some scalar function pi. So let me replace dq by dt with del pi into dx. So from equation 1 I have expressed the velocity vector as gradient of some scalar function. Clear? Now I can write del pi into dx as d pi. Del pi into dx as d pi. Hege andre, like del pi can be written as one second. See, look at here, del pi into dx, right? So I can write del pi as dou pi by dou x1 into I cap plus dou pi by dou x2 into j cap plus dou pi by dou x3 into k cap into dx is a vector. So dx1 into I cap plus dx2 into j cap plus dx3 into k cap. So scalar multiplication, vector multiplication. So corresponding components you are going to multiply. Dou pi by dou x1 into dx1 plus dou pi by dou x2 into dx2 plus dou pi by dou x3 into dx3. But these steps are not mentioned in the notes, so please go through it. So you can note that while explaining the calculus of tensor, I have explained this as a total derivative d pi, right? Like df is equal to dou f1 by dou x1 into dx1 plus dou f2 by dou x2 into dx2 plus dou f3 by dou x3 into dx3. This is what I have explained, right? So this is what the total derivative is. Here in place of f you have in pi, so that is why I can write this expression as d pi. So remember, integration over closed curve C, del pi into dx can be written as d pi. So that is what I have written here. So del pi into dx can be written as d pi, total derivative d pi. So just now I have told you integral over a closed curve is equal to 0. So dic by dt is equal to dic by dt is equal to 0, meaning is circulation rate of change of circulation is 0, is same as circulation remains constant, right? So circulation remains constant is same as the differentiation is equal to 0. Vice versa, I mean if you differentiate this, so dic by dt will be equal to differentiation of constant is 0. So this is what, from this expression we can say a circulation is constant around a closed curve C. This is what the Kelvin circulation theorem is, and this theorem is important. It has been asked in the year 2015 and 19. Hope you understand. Now the next concept is Rena's transportation formula. This is also an important question which is asked in 2015 and 18. I have considered a continuum at time t is equal to 0. This is what the initial configuration is. Let V0 be the volume occupied by the continuum at time t is equal to 0. So after some time t it moves to the some other point, so this is called as current configuration, and V be the volume occupied by the continuum when t is greater than 0 in the current configuration. And if dV0 is the volume of one of the element of a continuum in initial configuration, and dV is the volume of a sum of the element in a current configuration, then there exists some relation between these two volumes, like dV is equal to J into dV0. Fine. If dV is the volume of an element in a current configuration and dV0 is the volume of an element in the initial configuration, then there exists some relation like dV is equal to J into dV0, where J is the Jacobian transformation which I have explained in the previous class. Jacobian transformation, right? Now what I am going to do is, you can write your own explanation. So let me multiply some scalar function pi on both sides of equation 1 and integrate with respective volumes. In the sense, I will multiply pi to this equation on both sides and I will integrate with respective volume. So for element dV the volume is V, for element dV0 the volume is V0. What I have done is, I multiply scalar function pi and I have integrating it over the volume. So now I am going to differentiate the same. D by dt V pi dV is equal to d by dt V0 pi into J into dV0. Now I am going to manipulate the RHS. This is what the integration V0. Let me take this inside, d by dt of pi into J dV0. Now again a product rule, product of two function. I can write V0 first function into derivative of second function plus second into derivative of first function. Fine. First function into derivative of second plus second into derivative of first. Now from the Euler's formula just now I have defined. Euler's formula is given by dj by dt is equal to j into divergent of q. In the note I have given this. dj by dt is equal to j into divergent of q. This is what the Euler's formula is. Now let me replace here pi as it is. dj by dt I will replace with j into divergence of q plus j into d pi by dt into dv naught. Look at this, in both the terms you have j as common, so let me take j outside. So you will get v naught pi into divergence of q plus d pi by dt into j into dv naught. I have taken j outside, so this is what I have. Now from equation 1, look at the equation 1. Equation 1 is dv is equal to j into dv naught. So j into dv naught I can replace with dv, right? v naught pi into divergence of q plus d pi by dt, j into dv naught is dv. Now from the definition of material time derivative in spatial form, these steps are not mentioned in the notes, please note this, spatial form. So material derivative in spatial form state that d pi by dt I can express this as dou pi by dou t plus q dot del pi. I have derived this in the previous class, so refer this one. If you have the total derivative d pi by dt, I can write dou pi by dou t plus q dot del pi. Let me replace d pi by dt with this expression. From this we can write this expression as pi into divergent of q plus dou pi by dou t plus q dot del pi into dv. And one thing is that when you are converting dv naught into v, the integral also converting to v naught to v. Now I can rearrange this as, let me write this term here, dou pi by dou t plus q dot del pi, and I will write this here, one and the same. I will just arrange the terms. Now I can write these two terms as dou pi by dou t plus del dot pi q. I can write both the terms as something like this. Why? Because the product rule. See, first term, this is what the product of these two functions, like differentiation. First function, I'll write the step here. Look at this. Del dot pi q can be written as first function into del dot q plus second into del dot pi. See here, q del pi plus pi del dot q is none other than divergent of q, pi divergent of q. Here it is. So this is something like a product of two functions pi and q. So I can write the whole term as something like this. So from this I can write v dou pi by dou t plus del dot, let me write the step once again here, into dv. So in the LHS what you have, d by dt of v pi dv is equal to integral over v dou pi by dou t dv. I am going to split the integral. This is what LHS is. RHS I am writing again, pi q. So what I have done is I have written the LHS as it is, and for the RHS I have splitted this integral for each and every term. I have written the same here. Hope you understand. Now from the divergence theorem, which we use to convert a volume integral divergence of u dv is equal to surface integral u dot n cap into ds. This is what the divergence theorem which used to convert volume integral into surface integral. Now you have divergence of pi q here, so divergence of u here. In place of u you have pi q. So by applying this divergence theorem, I can write the RHS as dou pi by dou t dv plus, see here, in place of u I have to write pi q. Integral, volume integral I have converted the same in terms of surface integral by the theorem. So in place of u, let me write pi q dot n cap into ds. So dou pi by dou t dv I have written the same. Divergence of q can be written by using the divergence theorem as pi q dot n cap into dc. In the LHS what we have, d by dt of pi dv is equal to d by dt of pi dv is equal to dou pi by dou t into dv plus integral over s pi q dot n cap into ds. This is what we call Reynolds transportation formula. So you can know from this equation that this equation contains, from the equation itself you can say the rate of change of the integral of a function, the rate of change of integral of a function pi consisting of the local derivative. While explaining the time derivatives, I have explained this is what the local derivative, sum of the local derivative, and pi q is called as the flux across the surface. Pi q is called as the flux across the surface. So it contains a local derivative and the flux. Now up to here the derivation is, and sometimes the consequence is also asked. Let me see. See, the consequence is that what happens to this Reynolds equation. Let me write the Reynolds equation as it is. I am just copying the equation. Pi dv v is equal to integral over v dou pi by dou t dv plus integral over s pi q dot n cap into ds. This is what the Reynolds transportation formula we have derived just now. Now what happens to this equation? Suppose if pi is equal to 1, wherever pi is there, I'll just replace pi with 1. So when you replace pi here with 1, it becomes something like this. See, pi is 1. Derivative of 1 is constant is 0, so this term goes off, so volume integral will not be there. Let me skip the step. So second term goes to second term. Pi is equal to 1 into q dot n cap into ds. Now integration over v dv is v. It is not a closed curve, it is a volume integral. dv by dt is equal to integral over s q dot n cap into ds. Now you have a surface integral. By applying the divergence theorem, you have to remember the divergence of Stokes theorem since we are using it in all the derivation. So divergence of u is equal to surface integral u dot n cap into ds. I am converting the surface integral in terms of divergence, volume integral. So I can write this as dy by dt is equal to volume integral del dot q dv. I have converted the surface in terms of volume integral. So this is what the special case is. It is also asked if pi is 1. Let me recapitulate it once again. This is what the Reynolds transportation formula. I am replacing pi with 1. So d by dt v dv is equal to integral over s. Here at present you have v only, I am sorry. So this term as it is, pi is 1, derivative of 1 will become 0. Again pi is 1 into q dot n cap ds. So here surface integral you have surface integral. Volume integral goes off because derivative of 1 is 0. Now I am converting the surface integral into volume integral by the divergence formula, and this is what we obtained. Hope you guys understand.